We all know that for many, many years, steam has been one of the most common forms of energy used in industrial processes. It can be used for a variety of applications, such as space heating, driving turbine and steam engines, meeting heat requirements for industrial processes, for example, the manufacture of pulp and paper. Steam has the advantage that it contains a considerable amount of energy in the form of heat, and it can easily be piped from one location to another. Steam flows naturally from the point of highest pressure to areas of lower pressure. In this video, part of the Industrial Power series, we'll be looking at the production of steam and, in particular, study the construction of boilers or steam generators, as they are often called. Now, we normally think of steam as being produced at high pressure, but of course this is not necessarily so. For example, if we boil water in an open pan on the stove, the pressure is zero, or rather atmospheric pressure. Let's see what happens. As heat is added to the water, its temperature is raised and steam bubbles start to form within the body of water. These steam bubbles are lighter in weight than the surrounding water, and therefore they rise naturally to the surface. This movement is known as natural convection. As we add more and more heat to the water, more steam bubbles form, and the apparent level of water in the pan rises. This is because each steam bubble takes up more space than the equivalent amount of water. The opposite action occurs if we reduce the heat supply or cut it off altogether. In this case, the steam bubbles collapse, and the level of the water decreases back to its original level. This phenomenon is known as swell when the level rises, and shrink when the level decreases. We mention it now because it is quite an important factor in operating steam boilers under varying load conditions, and we'll be looking at this in more detail later. Let us return now to our pan of boiling water. As the rising bubbles reach the surface, they burst and steam is liberated, usually forming a vapor cloud above the water. If the pan is open, this vapor rises into the surrounding atmosphere and will probably be absorbed by the air, increasing the humidity. Of course, the main reason for boiling a pan of water is usually not to make steam, but to heat the water to boiling point, that is 212 degrees Fahrenheit or 100 degrees Celsius, as you know. If we wish to make steam for utilization, we will need to raise the pressure of the steam so that it flows from the source of production to where it is utilized. In the case of the open pan, pressure can be raised simply by placing a lid on the top of the pan. Now, as the steam is formed above the surface of the water, it cannot escape to atmosphere and pressure begins to rise. Why is this? Well, it's simply a matter of available volume. As each tiny portion of water is converted into steam, it requires much more space and quickly fills the area between the surface of the water and the closed lid. As more and more steam crowds into the limited space, its density increases and the pressure rises. In this situation, as we well know, the lid of the pan would soon be blown off by the rising pressure of steam. The actual pressure developed depends upon the weight of the lid. So we can already see the basic requirements for a simple boiler to produce steam. First, we need an enclosed vessel, which has to be built to withstand the proposed steam pressure. A steam line would be connected from the top of our boiler vessel to carry steam to the point of application, say a heating system. A stop valve is fitted into the steam line to provide some form of control over steam flow. The vessel must be filled with water to approximately the halfway point. Before startup, air fills the space above the water as the air vent valves are open to atmosphere. It is clearly necessary to provide heat, and for this hypothetical boiler, we will provide this by combustion of fuel below the vessel. Initially, the boiler is fired with the stop valve closed. This is to allow pressure to build up within the boiler. Initially, it takes some time for the temperature of the water to rise from ambient to the boiling point. Since the vessel itself will be heated, it is insulated to minimize heat loss to the atmosphere around the vessel. Eventually, steam begins to form above the water level, and the rising pressure forces air from the vents. The vent valves need to be closed when all air has been expelled and steam exhausts from the vent. This is usually when the pressure has risen to about 20 psig. You'll remember that the unit psig, or kilopascal G, indicates gauge pressure above atmospheric pressure. Now, as more and more heat is added, the pressure continues to rise. So what do we have to do when the pressure reaches its target level, say 100 psig? How can we control this? Well, we have two options. One is to extinguish the fire so that no further heat energy is added. In fact, if we do this, the pressure will start to fall again as the vessel loses heat, unless we can provide 100% insulation. The second alternative is to keep the combustion going but open the boiler stop valve, allowing steam to flow from the boiler to the heating system. Now, depending upon the amount of steam being drawn by the heating system, the pressure will begin to fall. In order to maintain the rated steam pressure, we will need to add more heat to the vessel by burning additional fuel. So it's clear that in order to maintain the steam pressure at the desired level, we must strike a balance between steam demand and fuel burned. But that's not all. I can hear many of you already saying, but what about the water level? Well, yes, you're absolutely right. By the time we start supplying steam to the heating system, we will have evaporated all or most of the water in the vessel. So as evaporation takes place, a means must be provided to continuously add water so as to maintain the normal operating level in the boiler. This water is known as feed water, and it's important to note that in order to enter the boiler, it must be provided at a pressure higher than the operating pressure within the boiler. This is the job of the boiler feed pump. The feed pump discharge is, in fact, the point of highest pressure throughout the power plant cycle, and a considerable amount of auxiliary power is required in order for the pump to do this job. From this hypothetical simple boiler that we've been studying, let us summarize the major components that must be provided in any boiler installation. These are the pressure vessel, built to withstand the operating pressure; heat insulation, to prevent loss of heat from the vessel to atmosphere; steam piping and a means of controlling steam flow; a combustion system, and a means of controlling fuel supply; a supply of high-pressure feed water, and a means of controlling water level in the vessel; air vents on top of the vessel to permit expulsion of air during startup. Of course, a modern steam generator is vastly more sophisticated and complicated than our diagram, as we shall see. But we are often reminded of these basic requirements when studying boiler construction. One boiler type which is not so different from our hypothetical boiler is the fire tube type. In this arrangement, the vessel is really a cylindrical shell with a large fire tube running down the middle. Water fills the space between the fire tube and the outer shell to a high level. Fuel and combustion air are supplied through the burner at one end, and combustion takes place inside the fire tube. As the hot combustion gas passes along the tube, heat is transferred through the tube wall to the surrounding water to cause evaporation. The gas is eventually exhausted to atmosphere through the chimney. Steam collects above the water level, and from here, saturated steam is piped to the utilization equipment. Feed water is supplied continuously through a control valve, which maintains the correct water level in the shell. Steam pressure is controlled by adjusting the fuel and combustion air supplied to the burner. Once again, we're looking here at a simplified arrangement. If you have this type of boiler in your plant, make sure that you study the specific details of your installation. The fire tube type boiler is generally used for relatively small, low-pressure applications, such as heating. For power plants, the most common type of boiler in use is the water tube boiler. We'll move on to look at this in the next segment, but first, it's time for a break. Please switch off the video now and review this material in your workbook. In the last segment, we looked at the fire tube boiler, where the hot combustion gas flows inside the tube to heat water which is outside the tube. The arrangement in the water tube boiler is the other way around. That is, the water is contained inside tubes, while the hot combustion gas flows on the outside of the tubes. One typical arrangement has a bank of water tubes connected between upper and lower drums like this. The tubes and the drums are made of heavy steel, sufficient to withstand the operating pressure of the boiler. The upper drum, often known as the steam drum, contains water at the operating level. During operation, steam fills the space above the water. The boiler tubes and lower drum are also full of water. As hot combustion gas passes over the first row of water tubes, heat is transferred to the water inside the tubes. The heat transfer is by conduction through the tube metal. Sufficient heat is added so that steam bubbles form within the water, and these rise to the steam drum. These tubes are often known as risers for this reason. They are also called steam generation tubes and even evaporation tubes in some locations. Conversely, the tubes on the other side of the drum are known as downcomers. These tubes are in an area of lower temperature gas, thus no steam bubbles form. Consequently, the water in the downcomer tubes is more dense than the water and steam mixture in the risers. Therefore, this cooler, heavier water flows down on one side to replace the rising steam-water mixture on the other. This is known as natural circulation. As the steam and water mixture enters the steam drum, separation occurs with the steam entering the upper portion and the water returning to the lower part of the drum. As steam is drawn from the drum, the water level tends to fall. To compensate, feed water is fed into the drum at a controlled rate to maintain the correct level. This arrangement of tubes is usually known as a convection bank because heat is carried over the tubes by convection. That is, it is conveyed by the combustion gas. Heat is transferred to the water by conduction through the tube wall. But in order to utilize the tremendous amount of heat which is released by the combustion of fuel, we also need to transfer heat by radiation from the flame. To accomplish this, a large number of tubes must see the fireball. In fact, the boiler is constructed so that the entire furnace or combustion chamber is surrounded by water tubes known as water walls. The tubes in each water wall are connected to common headers, top and bottom. Typically, water is supplied to the bottom headers by downcomers, and from here it rises up the water walls as steam bubbles form inside the tubes. On many boilers, downcomers run directly from the steam drum in the form of large diameter high-pressure piping, passing outside of the boiler casing and connecting to lower water wall headers. The objective of running the downcomers outside of the boiler is to prevent the feed water from picking up heat, which would reduce the effectiveness of natural circulation. Indeed, with very high-pressure boilers working at, say, 2,500 to 3,000 psi, it's more difficult to obtain natural circulation because there is not as much difference between the density of water and steam at these pressures. With this type of boiler, forced circulation is often employed so as to ensure that an adequate flow of water is maintained throughout the boiler tubes at all times. With the forced circulation system, large pumps are installed in the downcomers to force the circulation of water. But why are we so concerned about maintaining good circulation of water through the tubes? Well, just consider the fact that the temperature of combustion gas inside the furnace is in the range of 2,500 to 3,000 degrees Fahrenheit, and by comparison, the temperature withstand capability of the wall tube metal is about 900 degrees Fahrenheit. It is only the positive flow of water inside the tubes which conducts heat away quickly enough to maintain the tube metal temperature at a safe level. If circulation ceases for any reason, for example, a blocked tube, the metal will rapidly overheat and fracture within minutes. If at any time during operation the boiler suffers from lack of feed water and consequent loss of circulation, the fire must be extinguished immediately in order to protect the boiler tubes from damage. As we'll see later, all of this is arranged automatically as part of the boiler protection system. The steam and water mixture formed in the water wall tubes rises to be collected in the upper headers, and from here it passes into the steam drum. The steam drum is an important component of the boiler that has many functions. The first is to separate the steam from the water in the returning mixture. Mechanical separators are located along the inside of the drum to perform this task, which is usually achieved by centrifugal action. Steam enters the upper part of the drum, while the water falls to the bottom, joining the incoming feed water. This returning water, along with the additional feed water, then goes back into circulation once again along the following path. Down the downcomer to be distributed to bottom headers. From the bottom headers up the water wall tubes where steam bubbles form in the water. Into the upper headers, and from here into the steam drum, where steam is separated from the water to enter the upper part of the drum. At any particular instance, we may have, say, 70% of the water in continuous recirculation, with just 30% being evaporated into steam. Of course, we must add feed water to make up for this 30%, which has been converted into steam. The feed water is normally fed into the steam drum through an internal distribution header, which runs along the whole length of the drum. Distribution nozzles feed water into the drum, usually in the area of the downcomer pipes. The objective of this is to provide the cooler water to the downcomers and so improve natural circulation. The quantity of feed water entering the drum is controlled so as to maintain the desired water level in the drum. Usually, automatic controls carry out this task by adjusting the feed water control valve or perhaps the speed of the feed water pump. The steam which collects in the upper part of the drum is saturated steam and will be at saturation temperature. For example, if the steam pressure in the drum is at 200 psi, its temperature will be 381 degrees Fahrenheit. At a pressure of 1000 psi, the saturation temperature is 542 degrees Fahrenheit. The water in the steam drum will be at a slightly lower temperature due to the dilution effect of the entering feed water. Steam is drawn off the top of the drum, and to make sure that this is as dry as possible, another set of steam separators or dryers are fitted along the inside of the drum at this point. We do not want to carry droplets of water along with the steam if this can be avoided. So we can see that the steam drum contains quite a lot of hardware. And in addition to that, there are a number of very important external connections, such as one or more safety valves, which will open in the case of excess pressure inside the drum. Valved vent connections, which allow air to be expelled from the drum during startup when the pressure is rising. Chemical feed injection, which allows us to inject certain chemicals to control the quality of boiler water. A blowdown connection permitting continuous discharge of water in order to reduce the accumulation of solids in boiler water. Instrument connections for monitoring and control of boiler operation. Gauge glasses, usually fitted at each end of the drum, to provide a physical view of the water level in the drum. Steam connections from the top of the drum. Downcomer connections at the bottom of the drum. Means must be provided for draining the boiler of water in the case that certain maintenance work needs to be performed. For this purpose, large drain valves are fitted at low-level points such as the bottom drum, downcomer's low point, bottom water wall headers. Now, we'll be looking at all of these items in greater detail as we proceed through this program. But first, let's take a break, and then we'll come back and take a look at superheater arrangements and other components of the boiler. For now, though, please switch off the tape and thoroughly review this material in your workbook. In many industrial processes, saturated steam is quite adequate for the job at hand. In these cases, steam can be provided directly from the boiler steam drum. However, in many situations, it may be essential that dry steam is supplied. If the steam is used to drive a turbine, we would also like the temperature to be higher in order to improve the efficiency of the turbine cycle. For this application, the steam temperature typically should be 950 or even 1,000 degrees Fahrenheit, whereas the temperature of saturated steam is more likely to be about 550 degrees Fahrenheit, depending upon the actual boiler pressure. So clearly, for many applications, the saturated steam needs to be superheated. You'll remember we discussed this subject in the previous video in this series. Heat is added to the saturated steam by passing it through a bank of superheater tubes, which extend right across the boiler in the path of the combustion gas. Steam from the drum passes into the superheater inlet header, and from here is distributed to all of the superheater tubes. As the combustion gas leaves the water wall area, it enters the superheater zone. Here, heat is transferred by conduction to the steam, which is flowing inside the tubes. The temperature of the steam rises, and the temperature of the gas falls. Steam is collected from the superheater outlet header and fed to the boiler main steam line through a stop valve. A vital point to remember is that during operation, the superheater metal temperature is far higher than that of the water walls. This is because the temperature of the steam which is passing inside the tube is far higher, ranging from about 550 degrees Fahrenheit at the inlet section all the way up to 950 or 1,000 degrees Fahrenheit at the outlet. For this reason, superheater tubes are made of special alloys which are resistant to high temperatures up to a certain point. During operation of the boiler, a great deal of attention has to be paid to preventing over-temperature of superheater tube metal. The maximum permitted tube metal temperature is usually about 1,100 degrees Fahrenheit. So remembering that the temperature of the gas passing over the outside of the tubes is about 2,000 degrees Fahrenheit, it is clear that it is only the flow of steam passing inside each tube which keeps its temperature within safe limits. If for any reason this steam flow stopped in any particular tube due to a blockage, then the tube metal would rapidly overheat and rupture. This would then allow high-pressure steam to spill out into the gas passages. The type of superheater we are showing here is known as a pendant superheater. It is supported by hanging from the inlet and outlet headers and has ample freedom for expansion and contraction. One disadvantage of this type of superheater is that it is not drainable. For example, when the unit is shut down, the residual steam which is contained in the pipework and inside the superheater itself condenses to form water. This water collects in the lower portion of each superheater tube and so effectively blocks the flow of steam when the boiler is fired again. So during startup, we run the risk of overheating. The cure for this is to keep the gas temperature down by low firing until all of the water in the superheater tubes has been evaporated into steam, so that flow through the tubes can once again be established. Another way around this problem is to fit horizontal superheater tubes like this. With this arrangement, the drains on the lower header can be opened so as to completely empty the superheater during shutdown. One thing we have to remember is that when the boiler is started up, it is normal to have the stop valve closed while raising pressure. This means that even with the superheater drained, we will still not have natural flow of steam through the tubes, as there is no steam flow from the boiler. In order to create a steam flow, vents and drains are fitted at the superheater outlet header. No matter what type of superheater is installed, these valves must always be open during startup and must not be closed until the boiler is online, supplying steam to the turbine or other equipment. In many installations, the superheater is divided into two sections known as the primary and secondary. The primary bank of tubes will raise the steam temperature to about 750 degrees Fahrenheit, while the secondary superheater bank increases temperature to the rated value, say 950 degrees Fahrenheit. So this scheme actually provides two banks of superheaters in series. From the point of view of the steam turbine or other receiving equipment, we would like to have a constant steam temperature. On most boilers, there is a tendency for steam temperature to rise as output and consequently the rate of firing or energy input is increased. The steam temperature may also vary according to the state of cleanliness of the superheater tubes and water wall tubes. We'll be talking more about this later when we look at detailed operation. In order to prevent over-temperature and provide some degree of control, it is common to install a de-superheater. This injects a fine spray of feed water into the steam, leaving the primary superheater. This small amount of water is soon evaporated, but in doing so, it reduces the steam temperature at this point. This, in turn, is reflected in lower steam temperature at the secondary superheater outlet, that is, the exit steam from the boiler. The quantity of de-superheating water, or attemporation as it is known, is controlled according to the final outlet temperature required. Clearly, the de-superheater can only operate in one direction. That is, it prevents the steam temperature rising too high. But what can we do in the case where steam temperature is too low due to deposits of ash and soot on the superheater tubes? Well, to look after this problem, retractable soot blowers are normally installed in the superheater zone. These blowers are operated intermittently, say once per shift. During operation, the blower tube enters the boiler, passing across the bank of tubes while rotating and discharging a jet of steam or air to blow deposits from the tubes. As we'll see later, other types of soot blowers are also located at various points throughout the boiler. Where does the steam come from for soot blowing? Well, this may be saturated steam from the steam drum, but on some installations, steam from the primary superheater outlet is used. In many installations, compressed air is used instead of steam for soot blowing. On large boilers, we may have reheaters fitted as well as superheaters. Actually, the reheater closely resembles the superheater in appearance. Banks of tubes are placed within the path of the combustion gas in order to raise the temperature of steam flowing from the turbine and back to the turbine. The reheater tube banks are usually dispersed with the superheater banks because the temperature requirements are similar. For this reason, the type of alloy used for tube metal is similar, but the tube wall thickness is less due to the fact that the reheat steam pressure is much lower than the main steam pressure. In many boilers, some sections of the superheater are located in the upper furnace and consequently receive heat by radiation from the flame. However, most of the heat transfer surface for the superheater and reheater is located in the convection zone. In this area, most of the heat is transferred by conduction and convection. Water tubes may also be located in this area in order to extract as much heat as possible from the combustion gases before they are exhausted to atmosphere. We have yet further heat exchangers in the flue gas path, but we will look at these in the next segment. Now it's time for a break. Please switch off the tape and review this material in your workbook. Up to now, we've been concentrating our attention on the water and steam parts of the boiler. We looked at natural and forced circulation, water walls, the steam drum, feed water, superheater, and steam temperature control. Now it's time to look at the other side of the boiler, that is the combustion air supply and combustion gas path to the chimney. Now, we are not at this point going to discuss combustion fundamentals and burner equipment. This is a big subject which will be handled in the next video. But in order to complete our study of boiler construction, we should take a look at the supply of air to the boiler and the means of extracting gases from the boiler. The very basic fundamental of boiler operation is that we must provide fuel and air for it to burn. On small boilers, air is sucked into the furnace from atmosphere. The negative pressure in the furnace is created by natural draft from the chimney. Hot gas rises up the chimney by natural convection, thus drawing a slight vacuum at the bottom of the chimney and connected furnace. On all medium and large-size boilers, combustion air is provided by a large fan known as a forced draft or FD fan. On many installations, 2 FD fans are installed. The total quantity of air supplied must be regulated according to the amount of fuel being supplied and the actual firing conditions. The conventional way of adjusting forced draft is to adjust the opening of the inlet damper supplying air to the fan. The discharge damper is normally used for isolation only. Another adjustment method is to regulate the speed of the fan. Control is normally effected remotely and generally automatically, as we'll see later. Now, this total quantity of air may be delivered into the furnace via several different routes, depending upon the type of firing employed. In this oil-fired boiler, air is admitted into the furnace from a wind box through adjustable dampers around the burners. Once in the furnace, air mixes with the fuel to create combustion. The resultant combustion gas flows through the water wall chamber and across the superheater bank, and of course, reheaters if installed. The water wall construction in effect provides a box which contains the fireball and the products of combustion. On the outer side of the water walls, a thick layer of refractory insulation is installed so as to reduce heat loss to atmosphere. Remember, the temperature on the outer side of the water wall tubes will be similar to the temperature of water inside the tubes. That is about 450 to 600 degrees Fahrenheit. So the heat loss would be considerable without insulation. The insulation is held in place by the boiler casing, which is made of relatively thin sheet metal that has no structural purpose in supporting the boiler. In a well-insulated boiler, we can quite comfortably walk in the vicinity of the boiler without feeling excessive heat emitting from the casing. However, where insulation is faulty, we will feel the high temperature in the locale, and the boiler casing may glow red. Access ports are often provided to allow us to look into the furnace at strategic points and also to enter the furnace during maintenance shutdown. At each of these locations, the water wall tubes are curved around the entrance hole to allow access. Now let's look at the temperature gradient as the combustion gas flows through the boiler and out to the chimney. First, the combustion chamber. Flames in the fireball are at a temperature in the region of 3,000 degrees Fahrenheit, and these flames radiate heat to the water walls by line of sight. A large amount of the heat from combustion is transferred to the water wall, and consequently the water inside the tubes by radiant heating. Higher in the furnace, beyond the fireball, hot combustion gas continues to transfer additional heat to the water walls by conduction. This hot gas eventually passes into the superheater zone at about 2,500 degrees Fahrenheit, where heat is transferred to the steam. A convection bank of water tubes may be located after the superheater in order to recover more heat from the gas. The temperature of the combustion gas leaving the convection zone is usually about 700 degrees Fahrenheit. Often an economizer is located in this area to further lower the exit gas temperature. This heat exchanger heats the incoming feed water typically to about 400 to 600 degrees Fahrenheit, depending on pressure in the boiler drum. The actual feed water inlet temperature to the boiler drum has to be lower than the saturation temperature. Otherwise, some of the water would flash into steam and may interfere with the flow of feed water. The most common type of economizer construction has water passing inside a bank of horizontal tubes while combustion gas flows across the outside of the tubes. Generally, feed water enters at the bottom of the bank and exits from the top for direct connection into the steam drum. As with other parts of the boiler, the economizer is fitted with vents and drains so that it can be emptied for maintenance. During operation, the combustion gas exits from the economizer at a temperature of about 600 degrees Fahrenheit. So this gas still contains a considerable amount of heat, and we would like to recover more of this heat before discharging the gas to atmosphere through the chimney. In order to achieve this, an air heater is normally fitted. This heat exchanger is used to heat the incoming air by extracting heat from the exiting combustion gas. One type of air heater consists of a bank of tubes with gas passing over the outside of the tubes and air through the inside. A more common type is the rotary air heater. This consists of a series of thin plates mounted in a drum which rotates alternatively between the exit gas duct and the incoming air duct. As the thin plate sections pass through the hot gas duct, they pick up heat. And as rotation continues, this heat is transferred to the air. Seals are provided between the upper and lower sections of the rotating drum to prevent leakage between the air and gas ducts. We'll be talking about operation and care of the air heater later in this program. The combustion air leaves the air heater at a temperature of about 450 to 500 degrees Fahrenheit. Meanwhile, the combustion gas exits at a temperature of about 300 degrees Fahrenheit. In the most simple arrangement, exit gas from the air heater passes directly into the chimney and exhausts to atmosphere. The arrangement shown here uses one FD fan only. It must provide sufficient pressure to push the air through the ductwork, wind box, burners, combustion chamber, now as combustion gas, superheater zone, economizer, air heater, and up the chimney. All of these components offer resistance to flow and so create a pressure drop at each point. If we assume that the pressure at the bottom of the chimney is zero gauge pressure, we will find that as we move back through the system, the pressure has to increase to be the highest at the FD fan discharge. Clearly then, with this arrangement, all of the system, including the combustion chamber, is operating under a positive pressure. This is known as a pressurized furnace. Now, the pressure is not very high, perhaps in the region of half a psi, but even so, any small leakage within the ductwork or boiler casing will allow combustion gas to escape. So with this type of boiler, great care must be taken to make and keep the boiler gas tight. Special arrangements have to be made where access ports can be opened. To prevent escape of combustion gas from such areas, a supply of sealing air or aspirating air is injected around the open port in sufficient quantities to prevent leakage. Special sealing air fans are provided for this purpose. We'll be looking at the actual measurement of draft in the furnace and throughout the boiler later in this program when we discuss boiler operation. One way to prevent the problem of gas leakage from the boiler is to maintain the furnace and gas passages under a slight negative pressure. This is achieved by fitting an induced draft or ID fan in the gas exit ducting between the air heater and the chimney. This ID fan is sized so as to suck the gases to be discharged up the chimney out of the boiler. Maintaining the correct negative pressure inside the furnace is an important part of boiler operation, as we'll see later in this program. In situations where both forced draft and induced draft fans are installed, the system is known as a balanced draft system. Now, the system we've been studying here is quite basic and does not include any pollution control equipment. For example, if the boiler is coal-fired, it would be fitted with equipment to remove dust and other particulate matter from the gas stream before it is discharged to atmosphere. Flue gas treatment equipment may also be installed if high sulfur fuel is being burned. We'll deal with this subject in more detail in the next video. However, in this tape, we feel it's important to stress the major features of boiler design and construction. Now, this time, let's take a break, and then we'll come back and look at heat recovery boilers. For now, please switch off the tape and review this material in your workbook. Up to now, we've been considering that our boiler obtains heat by the combustion of fuel. But in many applications, particularly where cogeneration is involved, the heat is provided by high-temperature waste gas. This may come from several possible sources, such as the exhaust from a gas turbine, the exhaust from a diesel engine, waste gas, commonly known as off-gas, from an industrial process. The heat from this gas can be usefully employed to produce steam by passing it through a heat recovery boiler. The usual term for this type of boiler is HRSG, that is, heat recovery steam generator. In this type of boiler, the temperature of the gas entering is usually about 1,000 degrees Fahrenheit, and the exit gas temperature to the stack is about 350 degrees Fahrenheit. The heat is extracted from the gas by placing banks of tubes directly in the path of the gas flow. The tubes are often thinned to increase surface area and heat pickup. This cutaway diagram shows the major sections of the HRSG. The incoming gas first passes over the superheater and reheater sections. This, of course, is the area which requires the highest temperature. From here, it passes over the water tubes, which are connected to the steam drum. Steam generation takes place in these tubes, and this section is usually called the evaporation section. In this diagram, we see the downcomer from the steam drum feeding into the lower header of the evaporation section. Finally, as the gas temperature is decreasing, it passes over the economizer section to heat incoming feed water. Note that water wall construction is not used. This is because there is no fireball in the HRSG. Consequently, water wall tubes would not pick up much heat. Remember that in the fired furnace, much of the heat transferred to the water walls is by radiation from the flame. As there are no water walls, the steel casing of the HRSG must be very well insulated so as to prevent heat loss to atmosphere. The HRSG also works under positive pressure from the gas turbine or diesel engine exhaust. The tube banks must be designed to provide the least resistance possible to the flow of gas. Otherwise, back pressure on the turbine or diesel engine exhaust will reduce the efficiency of these components. The function of the components of the HRSG are the same or similar to the fuel-fired boiler. Feed water passes first through the economizer in order to increase its temperature before entering the steam drum. The water then passes through the convection banks of the evaporator section where steam generation takes place. The steam-water mixture returns to the drum where it's separated. Steam then passes out to the superheater where additional heat is added, and from here it flows to the utilization equipment. Also, similar to the fired boiler, auxiliary devices and equipment are fitted, such as safety valves, drains and vents, gauge glasses, water level controls, continuous blowdown line, chemical injection feed, monitoring equipment. In some installations, a gas bypass is provided around the HRSG, complete with associated dampers. The main objective is to allow the gas turbine to continue operation when the HRSG is isolated and removed from service for maintenance. Another advantage of the bypass system is that it allows some control over the rate of heating and raising pressure of the HRSG during startup. During the startup, some of the gas can be bypassed, thus reducing the quantity of heat transferred to the HRSG. The bypass could also be partially opened if the steam demand on the HRSG fell below its rated output. In other words, we would probably find it more economical to waste some of the heat in the gas than to reduce the load on the gas turbine. But what about the other problem, where the steam demand is greater than the equivalent gas turbine load? Say, for example, that the gas turbine is limited in output by a fault in auxiliary equipment. This would, of course, reduce the output of the HRSG. In order to overcome this problem, oil or gas-fired burners are sometimes fitted into the inlet ducting ahead of the HRSG. With this arrangement, more heat can be added to the gas and the temperature raised so as to maintain or even increase steam output. However, we prefer to think of the burners as ancillary equipment for use under special circumstances only. As we've said before, the temperature of the gas entering the superheater zone is generally about 1,000 degrees Fahrenheit. This is far less than the gas temperature entering the superheater zone of a fired boiler, which is usually in the region of about 2,000 degrees Fahrenheit. This lower temperature in the HRSG means that the boiler tube metal is subject to less temperature stress, and this usually allows a faster startup of the HRSG. Another feature of the lower gas temperature is that it effectively reduces the superheat steam temperature that can be achieved from the HRSG. Most HRSGs operate with a final steam temperature of 850 to 950 degrees Fahrenheit. In order to make use of this gas at the lower temperature end, it is quite common to construct a HRSG which incorporates several independent pressure levels. For example, just looking at the external view of this HRSG, we can see that it has 3 steam drums. That is the HP, or high-pressure steam drum, the IP, or intermediate pressure steam drum, and the LP, or low-pressure drum. Let's look at the internal arrangement, beginning with the low-pressure section. This operates at a steam pressure of 100 psi and has no superheater or economizer. Feed water is fed directly into the drum and from here through the convection banks of the LP evaporator. Saturated steam is produced at the saturation temperature of 328 degrees Fahrenheit. This steam is used for space heating. Now, let's look at the intermediate pressure system, which operates at 400 psia. Note that the incoming feed water must have sufficient pressure to overcome the pressure in the steam drum. In this case, the feed pump is delivering 600 psia to the control valve. Feed water passes through the IP economizer and into the drum. Steam is produced in the evaporation section and rises to the top of the drum. From here, saturated steam is passed through the IP superheater, exiting at a temperature of 700 degrees Fahrenheit. This steam is then delivered to the industrial process in the plant. Let's now add the high-pressure section, which operates at 800 psia. Again, feed water passes through an economizer on its way to the HP drum. Steam is generated in the evaporation section and rises to the top of the drum. From here, it passes through the HP superheater, exiting at a temperature of 950 degrees Fahrenheit. Here, this high-pressure steam supplies a small steam turbine generator. Now, at this point, it's time for you to study your own HRSG where this is appropriate. If your installation includes or consists of fuel-fired boilers, then take a good look at the components to see how they compare with the arrangements discussed in this video.